To talk about electric currents, let's start off by refreshing ourselves with something we are already familiar with, gravitational potential energy. So imagine we have a system that has two reservoirs of water. We have an upper reservoir full of water, then water flows from there into the lower reservoir, and as it flows, it turns a water wheel. Very simple. Now let's look at this in terms of energy. If we look at the upper reservoir, since it has a height, then we can say this upper reservoir has potential energy. And then as it flows into the lower reservoir, that water is now moving, and so it has kinetic energy. And that transfer from potential energy to kinetic energy does work, and that work is manifested through the turning of a water wheel. Now, the transfer from potential to kinetic energy in this example is what we call a current or a flow of water. Okay, with this stage now set, we're ready to look at electric potential energy. Instead of gravitational, we're going to use the same analogy to describe electric potential energy. So we have a voltage source, a battery, and conducts electricity through a light bulb. So what happens is we have the battery, which is a source of potential energy, and then the potential energy is used in the light bulb. That's where work is done, not exactly kinetic energy, but related to it. So your work is done in the light bulb. In order to go from potential to getting the work done, we need some sort of a current. This current is a flow of electric charges. And this is the definition of electric current, the flow of electric charges. So let's take a look at numbers for electric current. Since electric current is the amount of charge, the rate of flow of electric charge, the way we calculate it would be the quantity of charge moving per time. So for instance, we have in our figure here, 1 coulomb of charge moving every second. That is the definition of 1 ampere, or in short, 1 amp. So when you look at a device that you hear it talking about, say, running at 50 amps, that means 50 coulombs of charge flowing per second. Let's take a closer look at the current itself. Let's say that we have a positive charge on the left of this battery and a negative charge on the right side of the battery. If you were to place a positive charge anywhere in this circuit, that positive charge would flow away from the positive charge, the positive terminal, flow towards the negative terminal. But at the same time, any negative charges in this wire will flow away from the negative terminal towards the positive terminal. So at the same time, you have positive charges moving one way and negative charges moving the other way. That's happening simultaneously. So what direction do we indicate for current, since there's motion in both directions? Well, just as we did with electric fields, remember we did electric fields would be the direction a positive test charge moves in that field. We're going to do the same thing here and talk about the direction a positive charge moves in an electric current. So convention says we draw the current going from the positive terminal towards the negative terminal. There's one more principle that is very important in electric circuits, and that is resistance. Resistance is a property of opposing or reducing a current. If we were talking about, say, moving an object along a floor, then the equivalent of resistance would be friction. Friction opposes motion just in the same way that resistance opposes the flow of charge or electric currents. Whenever you have resistance, this causes a loss of electrical energy, say in the form of heat or light. That would be the case of a light bulb. You have a little filament which has very high resistance, so high that the energy is transformed from electrical energy to light or heat. And the way we measure resistance is in the unit of ohms. And that's this little Greek letter omega. So anytime you see that symbol, we're talking about how effective an object is at resisting electrical currents. Now, what determines the resistance? There are four main things that determine how well an object resists electrical currents. First of all, the type of material. The material is very important. For instance, copper is a very good conductor, very, very low resistive properties. Whereas on the other hand, say styrofoam, just to think of one offhand, very high resistance factors. So the material itself, it has a huge has a huge role in the total resistance. The length of the conductor also determines the resistance. A 1 meter length of copper wire will have far less resistance than, say, 20 meters of copper wire. The cross-sectional area, if you have a thick wire, that allows for more charge to flow, so you'll have less resistance. Whereas if you have a very small wire, a very thin wire, it doesn't allow electricity to flow quite as readily, so you're going to have higher resistance. Believe it or not, temperature also has a huge role, and we make use of that. One place where you can see the relationship between temperature and resistance is in a thermometer in any car. When you turn on a car and it tells you that the temperature outside is 76 degrees, it knows that by measuring the resistance of a wire in the car. Now there is something called a superconductor. A superconductor is a material whose properties allow the resistance to drop to zero or negligible resistance. Now this only happens at low temperatures. So the colder these metals are, the lower the resistance is, to the point where resistance is negligible. These are superconductors. Now, there are a few different ways we can arrange resistors in a circuit. The two main ways are series, which is you take the resistors and you connect them in a straight line. If we do this, then all you have to do is take the resistors and add them together. For example, if we have 3 lamps that are 10 ohms, 20 ohms, and 30 ohms, then the total resistance would be 10 plus 20 plus 30 is 60 ohms. All right. The other setup would be a parallel circuit. In this case, you have resistors not in one single line, but in branching lines. The line branches into three or any number of different paths, and one resistor is placed in each path. In order to add these, in this case, instead of just adding up the resistances, we need to add up the inverses. So once again, if this is 10 ohms, 20 ohms, and 30 ohms, then we need to take the inverses, 1 over 10 plus 1 over 20 plus 1 over 30. This would be 3 over 30 ohms, just to use our common denominator. Hang on, we need to get a common denominator, and 20 doesn't go into 30, so let's try that again. Our common denominator in this case will be 60, so this will be 6 over 60 ohms plus 3 over 60 ohms plus 2 over 60 ohms. Basically 10 times 6 is 60, so the top has to be 6. 20 times 3 is 60, so the top has to be 3. 2 times 30 is 60, so the numerator has to be 2. So 6 plus 3 plus 2 gives us 11 over 60 ohms. But remember, that's 1 over the total resistance. So the actual resistance, we have to take the inverse of that again. 60 divided by 11, which turns out to be 5.45 ohms. Now, the way that voltage and current and resistance are related is a principle we call Ohm's law. Basically, the voltage you have on a circuit is going to be equal to the product of the current and the resistance. Now, this leads to 2 very interesting relationships. So here's our equation, V equals IR, voltage equals current times resistance. Now, if we were to increase the voltage and leave the resistance the same, then the only way to do that is if the current increases as well. Increase the voltage, increase the current if the resistance stays the same. Recall, this is what we mean, this is the definition of being directly proportional. So current is directly proportional to voltage. Now let's take the same equation. This time let's leave the voltage alone. But instead, let's increase the resistance. If we increase the resistance, the only way to keep our equation balanced is if the current decreases, which means that current and resistance are indirectly proportional. Now, a word on electric power. Recall from before that power is the rate of energy usage, the rate at which we use energy. And the way we calculate it is the amount of energy used per time. So if we were to work with that a little bit, massage the equation a little bit, it would come out that electric power is the product of current and voltage. P equals IV, power equals current times voltage. And electrical power is often given in either watts or kilowatts. Now, when we use electric power, say in our homes or at our businesses, we have to pay for it. How are we going to know how much electricity, how much we owe for power usage? Just to be clear, we're actually not paying for power. Power is just the rate at which we use energy. What we're paying for is energy itself. And so if power is equal to energy times time, then energy is going to equal power times time. So we need to start off by finding the amount of energy that we use and multiply that by the rate of the cost rate. And so the total cost will be the amount of energy we use, power times time, times the rate. So let's take a situation where we have a 75-watt light bulb running for 3 hours and 20 minutes. The power company charges at a rate of 12 cents per kilowatt hour. So we want to know how much does it cost in this scenario. So again, our power is 75 watts. But notice our cost is in kilowatts and hours, so we want to write our power in kilowatts. Remember, kilo means 1,000, so we divide by 1,000, and we get 0.075 kilowatts. And the time it takes is 3 hours and 20 minutes, which transcribes to 3 1/3 hours, or 3.33 hours. So our equation is that the cost is going to be the power times the time times the rate at which we use, the rate at which the power company charges. So the power is 0.075 kilowatts times the time, which is 3.333 hours, times the rate, 12 cents. Now, if we multiply the power times the time, we get the total amount of energy Plugging that into a calculator, we find that the total amount of energy we've used is 0.25 kilowatt hours worth of energy. And again, we have to multiply that by 12 cents since we have 12 cents per kilowatt hour. Multiply that together, and you get a total cost of 0.03. In other words, that's 3 cents to run a 75-watt light bulb for 3 hours and 20 minutes.